Hello and welcome to this week 7 TS session on constraint and unconstrained optimization. So we'll be starting with the nonlinear optimization portion of this course, and I'll be first solving the week 7 assignment problems. I know that have been already solved by you, and I think the answer keys and everything are out, but still I'd like to solve them because it's a week 7 class, and after that I'll go and discuss the similar problems that are there in week 8 assignment. So without further delay, I'll get started with today's content. So as I have already mentioned, the topics that I'll be covering, I'll write it down. So the first topic that I'll be covering are the week 7 assignment solutions. And the second topic will be a similar problem to week 8 assignment. If there is enough time, I'll discuss this. And if there is anything remaining, I'll cover it in the next week's lecture or the TS session. So let's get started with this week 7 assignment solutions. Okay, so let me write down the first problem and I'll then solve it. Okay, so the first problem states that if f of xyz equals c1 times x square y to the power 4 z to the power 5 plus c2 x y square z to the power minus 2 plus c3 z cube. Okay, then which of the following statements is correct? Then which of the following statements is correct? Okay, so let's answer this. First I'll write down the options, then we'll discuss. So the first one says that fxyz is a polynomial if and only if c2 equals 0. Option B tells you that fxyz is a polynomial if and only if c2 equals 0 and c1 c3 equals minus 2. Option C tells you that fxyz is a polynomial irrespective of the value of c2 and finally option D tells you fxyz is a polynomial if c2 equals minus 2. Okay, so let's look at these options one by one and see which one will be the correct one. So let me write down. So first I'll write down this expression. Sorry, it will be z to the power 5. Then I have c2 x y square z to the power minus 2 plus c3 z cube, right? Okay, so now if c2 equals 0, we get fxyz equals c1 x square y to the power 4 z to the power 5 plus c3 z cube. So all the the powers of this xyz terms are positive integers here. So this implies that this becomes a polynomial. So option A is true. So A is true. Then option B says that it is a polynomial if and only if c2 equals 0 and c1 c3 equals minus 2. As we have seen that for c2 equals to 0, it's a polynomial. So even if you set c1 and c3 to minus 2, it will remain as a polynomial. So option B is not true. Option C, it says that it is a polynomial irrespective of value of c2. But you can notice that this term has a negative coefficient, which is minus 2, right? Z to the power minus 2. So that means if c2 is non-zero, this will not be a polynomial, but it might be a polynomial or something else, depending on the values of the coefficients. So option C is also not true. Finally, you have this option D, which tells you that if xyz is a polynomial if c2 equals minus 2, which is also not true because in that case, so the definition of polynomial tells you that the c coefficient should be positive, right? So it cannot be negative. So option D is also not true. So it's only option A which is true here. So the answer to this problem is option A. Okay, so I hope this will be clear to you. So that's the first problem that I have solved. Now let's move on to the second problem, and I'll write it down and then I'll solve it. So the second problem tells you that find the values values of C, Q, small q and then capital Q when the quadratic function fx1 x2 equals 5 plus 4x1 plus 6x2 plus 2x1 square minus 4x1 x2 plus 2x2 square is written in the standard form of f of say capital X equals C plus Q transpose capital X plus half capital X transpose capital Q capital X. Okay, so let me solve this. Okay, so here what is capital X? Capital X is nothing but your small x1 x2, so this is just a vector form. So you can write f of capital X, which is 5 plus 4x1 plus 6x2 plus 2x1 square minus 4x1 x2 plus 2x2 square. Okay. Also, it is given that f of capital X is C plus small q transpose X plus half of capital X transpose Q of capital X. Now, what you can do here is that capital X expression of capital X is known. Small q is nothing but it's Q1, Q2. C is a constant and the capital Q is nothing but, so it will be a composed of 4 terms, so you can assume it like this. Okay, so now we plug this in here, so it is nothing but C plus, so you can write it as Q1, Q2, so it becomes a row vector, and then you have this x1, x2 plus half, then you have x1, x2, then you have this matrix, 2 by 2 matrix, and finally you have this x1, x2. Now you kind of simplify this, so this is C plus Q1 x1 plus Q2 x2 plus let me do this half times, so it's R1 C1, okay, Q1 x1 plus Q3 x2, and it's a row vector, so it will have another expression which I'll write it down on the bottom. Okay, let me it will be clear to you if I write it down separately. Plus half, it's sorry, Q1 x1 plus Q3 x2, then you have Q2 x1 plus Q4 x2, and this is x1 x2, then you have C plus Q1 x1 plus Q2 x2. Is my write up appearing? Yeah, it's now appeared. Let me check if I'm recording. Okay. Plus half times it will be Q1 x1 square plus Q3 x1 x2. That's another term will be Q2 x1 square. Okay. Sorry, it will be multiplied with the second term, so it will be Q2 x1 x2 plus Q4 x2 square. Now write it as C plus you can write it as just the terms of this small q1 x1 plus q2 x2, then you will have the terms of half q1 x1 square plus half q2 plus q3 x1 x2 and plus half q4 x2 squared. Okay. Now, since capital Q is a symmetric matrix, since capital Q is a symmetric matrix, we have q2 equals q3, and you can write this expression as equals to this 5 plus 4x1 plus 6x2 plus 2x1 square minus 4x1x2 plus 2x2 square. Okay, so what you have here, c equals 5, q1 equals 4, q2 equals 6, capital Q1 equals 4. Then you have Q2 equals Q3, so that will be minus 4, both will be minus 4, and finally Q4 equals 4. Okay, so what you will get, so that means you have C equals 5, Q equals 4, 6, and capital Q equals 4 minus 4 minus 4 and 4. Okay, so let's see which option is correct. So option A is not correct, whereas capital Q is different. Option B is not correct. Option C is also not correct. Yeah, option D is the correct one. So yeah, your answer will be option D. Okay, so that's the second problem. So I think it was also pretty simple. So let me move on to the third problem. Okay, so the third problem tells you which of the following is or are true about the function fx equals x cubed minus 9x squared minus 48x plus 52. Okay, and the options are x equals to 8 is local maxima. Option B is x equals minus 2 is local maxima. Option C is x equals 8 is a local minima. And option D is x equals to minus 2 is a local minimum. Okay, so let me solve this problem now. So what I have here is that fx equals x cubed minus 9x squared minus 48x plus 52, and for finding this local maxima or local minima, I need to test the first derivative as well as the second derivative, and according to that I can make decisions, right? So let me evaluate this first and second derivative. So this is 3x squared minus 18x minus 48, and the second derivative is 6x minus 18. Now set f prime x equals 0 to get the stationary points. Okay, so this is 3x squared minus 18x minus 48, which is 0. So you can take 3 out of it and we'll be left with this will be 16, right? Okay, so this will be x times x minus 8. Okay, so that means x equals to 8 and minus 2 are the stationary points. Okay, so now plug this into that equation. So if double prime 8 is 6 times 8 minus 18, which is greater than 0. If double prime minus 2 is 6 times minus 2 minus 18, which is less than 0. So this will correspond to local minima and this will correspond to local maxima, right? So let me see which options are correct. 8 is local minima, so option C is correct, and minus 2 is the local maxima. Minus 2 is the local maxima, yeah. So option B is correct. So answer is option B and option C. Okay, so that's all about the third problem, and it was again straightforward. Now let me solve the fourth problem. Okay. So the fourth problem again tells you to solve a similar problem. So again I'll write it down. Which of the following is or are true about the function if x equals 3x to the power 4 plus 4x cubed minus 12x squared plus 12. Okay, so the options are option A is x equals 0 and 1 are local maximas. Option B is x equals 0 minus 2 are local maximas. Option C is x equals 0 and 1 are local minimas. Option D is x equals 1 minus 2 are local minimas. Okay, so these are your 4 options and let me solve this. So I'll write down the function. Fx is 3x to the power 4 plus 4x cubed minus 12x squared and I have plus 12, right? So this is the expression of the function and the first derivative is 12x cubed plus 12x squared minus it's not 12, it will be 24x. Okay, and the second derivative is 36x squared plus 24x hope this is correct minus 24. Okay, so now we have to set this f prime x to 0. So that will give me 12x cube plus 12x square minus 24x equals 0. We can take 12 out. So that's x cube plus x square minus 2x equals 0. It will be x times x square plus x minus 2 equals 0. And this can be written as x squared plus 2x minus x minus 2 equals 0. It will be x times x plus 2 and x minus 1 equals 0. So x equals to 0, 1 and minus 2 are the stationary points. Now I have to do the second derivative test. So f double prime 0 is minus 24, which means it's a local maxima because it is less than 0. Then f double prime 1, this is 36 times 1 squared plus 24 times 1 minus 24, which will be 36, which is greater than 0, and that means it's a local minima. And finally I have minus 2 here, so it's 36 times minus 2 square plus 24 times minus 2 plus minus 24, right? This is fine. This is also greater than 0, so that means this is a local minima. So 1 and minus 2's are local minima. So that's option D is correct. And which one is the local maxima? 0 is the local maxima. But the other option also contains those extra things, 1 and minus 2. So those are not true. So answer is D here. So that's only one answer. Okay, so that's all about this fourth problem. Now let me move to the fifth problem. So the fifth problem states that which of the following is or are true about the function fx equals x to the power 1 by 3. Okay. So option A is x equals to 0 is a point of inflection. Option B is the function has no point of inflection. Option C is x equals to 0 is a local minima. And option D is x equals to 0 is a local maximum. Okay, so let me solve this. So in order to get this local minima, local maxima, we have to anyway do this first and second order derivatives, and also for the point of an inflection thing we have to do the second derivative test, and if it is 0 and the third derivative, I think So if the second derivative is 0, then it's a point of inflection, but again it depends on whether the third derivative is non-negative, sorry, non-zero or not. Anyway, let me write down the function expression, which is fx equals x to the power 1 by 3. So let me check how to solve this problem. Yeah, so this f prime x is 1/3 of x to the power minus 2 by 3, and f double prime x is 1 by 3 times minus 2 by 3 times x to the power minus 5 by 3. Okay, so it will be minus 2 by 9 x to the power minus 5 by 3. So what you can do, you can set f prime x equals 0. So it's 1/3 of x to the power minus. So it gives you x equals 0. Okay. Yeah, so this problem has one issue here, because actually when you have this negative powers, so it's 1 by 3, 1 by x to the power 2 by 3, right? But when you set x equals to 0, so it becomes 1 by 0, which is kind of infinity. So it's not actually 0, but I don't know why the problem is given like this and why it is set like this. So that's one flaw I found in this problem, and as well as the next one that I'll be discussing. But anyway, let me check how they solved it. Okay, so what they did is, since it's a negative power, uh, so okay, so actually you cannot say anything about when it is 0, so this is not correct. Now when you have because x appears in the denominator. So that's the doubt I have here, but anyway, how you can solve it, you can probably take this expression of this second derivative and say epsilon is a small positive number, and what you can do, so this will be minus 2 by 9 epsilon to the power minus 5 by 3. So this is so this will be for epsilon greater than 0, right? And you can have another thing, and which is also very close to 0. For this one, what you will have is let me do it this way. Okay, anyway, so again it is tricky how it becomes this negative power is there, and how we are dealing with the negative value here, right? So I don't know how the solution is given, but I don't think the solution that is given is at all convincing. So there is this doubt here. Or should I write? Actually, cannot say anything like this. But anyway, for this one, what I have is this value is less than 0, right? And for the other one, it might be greater than 0, but again, it's not convincing. But anyway, if double prime 0 is, you put the value of x as 0. So if this is 0, then you can say something about point of inflection. So that's what is being done here. Then write it as okay, and that's how the answer is option A. But this is not at all convincing, right? So actually, let me take another example. 6 to the power 3 would be an example. So extra example here. Okay, so let me write it down. Suppose fx equals x cubed. Then what happens is that f prime x equals 3x square. F double prime x is 6x. F triple prime x is 6. Now, what you can do, f prime x you can set to 0, and that gives you 6x square equals 0, and x equals to 0 is the stationary point. Okay, now f double prime 0 is also 6 times 0, which is 0. F triple prime 0 is 6, which is greater than 0. Now you can also check f double prime epsilon, where epsilon greater than 0 is a very small positive number. It is 6 epsilon, so this is greater than 0, and this is minus 6 epsilon, so this is less than 0, so there is changing of sign. So that means x equals to 0, it is neither local minima nor a local maxima. Okay, so what you can say is that x equals to 0 is the point of inflection, because the second derivative is 0 and the third derivative is non-zero. Or should I think the spelling of inflection is confusing here. So that's the actual thing that you have to do during this finding out this point of inflections. But I don't know why this problem and the next one is given like this with some negative powers. Means the negative powers will appear somewhere, right? So that's the tricky part here. Or you can think about it like okay, so let me check with this. So fx is x to the power 1 by 3, right? So if I take the value as 0, then it's neither local maxima or local minima, because you can always take, say, a positive number and the value will keep on increasing, and a negative number then the value will keep on increasing, right? But again, when you take a negative number, that's the tricky part, right? How would you really evaluate minus 2 to the power 1 by 3? It's a fraction power and the value is negative, right? So that's the tricky part. Anyway, so let's not deal with this anymore because I personally feel there is some flaws with this problem, but anyway, let me go into the sixth problem, and which is similar flaws, right? Okay, so the sixth problem tells you find the point or points of inflection of the function fx equals x to the power 2 by 3 x minus 1 to the power 1 by 3. Okay, so the options are okay, the options, I'll write it down anyway. X equals to 0, 1 are the points of inflections. Option B is x equals 0 is the only point of inflection. It's the only point of inflection. Option C is x equals to 1 is the only point of inflection. And finally, option D is neither x equals 0 nor x equals 1 is the point of inflection. Okay, so let me solve this problem now. Fx is x to the power 2 by 3, x to the power minus 1 by 3. So again the issue occurs when you take suppose 0, then x equals to 0, so what happens to the other term, right? Or if when you take x equals to say 1, then there is something tricky as well. Okay, so not something like very like less than 1, then the tricky part becomes, the second part becomes negative, right? Okay, but anyway, the problem is given like this, so let's try and see, or rather approach the problem. So this will be plus okay, so rearranging it, plus 2 by 3 x to the power minus 1 by 3 x minus 1 times 1 to the power 1 by 3, right? So now let's get into the second derivative of this. The second derivative will be I'll do it in similar fashion. Okay, plus okay, And then this term 2 by 3 . Finally, it's 2 by 3. It's 4 by 3. Okay, so rearranging this will give you minus 2 by 9 x to the power 2 by 3 x minus 1 to the power minus 5 by 3 plus 2 by 9 x minus 1 to the power minus 2 by 3, or first I'll write down the x term, then the x minus 1 terms. So it will be x to the power minus 1 by 3, x minus 1 times to minus 2 by 3. Then, sorry about that. Okay. So it's the same term appearing twice, I guess. Okay, I think I made one mistake. Or is it? Okay. Okay, I think this is fine. The calculation should be fine, right? And the final term will be minus 2 by 9 x to the power minus 4 by 3 x minus 1 to the power 1 by 3. Okay, so actually you can combine those two terms and add it and write as 4 by 9 times those two things, but that is also fine. But now the tricky part comes in, right? So how do you approach this? So when you put x equals to 0, what happens is that some terms becomes negative, and yeah, it's tricky to even. So x equals to 0 lets you x equals to 0, you cannot say anything about about f double prime x. But when x equals to 1, then what happens is that you have f double prime 1 equals minus 2 by 9 times 1 to the power 2 by 3 into 0. Then the second term will also be 0. The third term will also be 0, and the fourth term will also be 0. And because there is no negative terms involved here. So that's why you can write it. So if double prime 1 is 0 and if prime 1 is also 0, and I don't know what will the expression of the higher order terms look like, but anyway, this is neither a minima nor a maxima from this. So what you can write is that x equals to 1 is the only point of inflection. That's the most closest, like it's the closest to the solution that I can think of, but again it might happen that neither x equals to 0 nor x equals to 1 is the point of inflection, right? So, but I don't know why the answer is given as C, because this problem again as before has some flaws, but okay, I'll write the answer as C, but the problem has some issues. Anyway, let's not get into the details of it. I don't know whether they will evaluate this problems anyway, but let me check one more thing. Uh, just a minute, I'll just check one thing. Start solving the next problem. Okay, so okay, so just a minute, I'll check a few things. Okay, just a minute, I'll just check whether the options are in this order or not. I think I opened the solution file. Yeah, I'll just check week 7 assignment problems. Yeah, so 1 is A, 2 is D, so that's fine. 3 is B and C, so that is also fine. 4 is D, so that's also fine. 5 is A and 6 is C, right? So that's what I did. Okay. Okay, so I think that's fine. Okay, so that's all about this sixth problem. I'll move on to this seventh problem now. So let me open the file again. Just a minute. Okay, so it says solve the, so I'll write down the seventh problem. So it says solve the optimization problem graphically. Problem graphically So the problem that is given is max of z equals 2x plus 3y, and this is subjected to x squared plus y squared less than equals 20, xy less than equals 8, and xy greater than 0. And yeah, options I'm not writing it down. I'll just later on I'll tell which one is the correct one. But anyway, start solving it. So what you can do, so the problem is given. Now let me draw the figures, the objectives and the constraints. So let me draw the constraints first. So this is x-axis, this is y-axis. Okay. So first you have x squared plus y squared less than equals to 20. So that's a circle centered around the origin, right? I ignored my drawing skills, but yeah. So this is root 20, 0 minus root 20, 0. This is 0, minus root 20. This is 0, root 20, right? So these are the points. And this entire, this is the origin, this is center. So let me, what I can do, this is the shaded portion. Then you have xy less than equals, or first I'll just write, so these are positive. That's this portion which you will take, and then you have xy less than equals to 8. So that's xy equals to 8. I think it's a curve of, it's a hyperbolic function. So again, drawing it will be a bit tricky, but anyway, 0, 0 will be a part of it. And so what you can do, so the curve I think will look like, let me draw it, saying some green mark. Yeah, probably, so in this portion it will look like this. And I think it will intersect, and the level set is kind of given like this. So this is the straight line 2x plus 3y. And these will be parallel level sets, right? So I'm not drawing the parallel lines here because I have to find the maximum. So graphically this will be the maximum point, but anyway, first I'll write down the coordinates, right? So the green, so this curve here, this intersects with the circle and it will be 2, 4. So that's 2, 4, xy equals 8, and also the circle will have this point 2 square plus 4 square, so that's fine. And through this, the straight line should pass, right? And when you have this point as 2, 4, then at that point, the value of the straight line is 2x plus 3y, so that will be 2 to the power times 2 plus 3 to the 3 times 4, so that's 16, right? And this curve will have another point. So 4, 2 will be another point which touches the or intersects with the circle, right? So I think this point will be 4, 2. So the good thing about it is that so you're maximizing it, so that's the most you can shift, and it's the less than equals region, so that means the actual region will be this one. So this is the feasible region, and the straight line touches there. So that 2, 4 point will be the optimal point here. So graphically you can do this. So x star, y star, it's 2, 4, and z star is 16. So your answer is A. Yeah, it's a bit tricky to solve it using graphical method, but that's the best you can do. You have to draw this hyperbolas and this hyperbola circle and then the straight lines and check where it touches the circle and hyperbola, and based on the feasible region you have to solve it. Okay, so that's all about problem 7. Now I'll go into problem 8. Yeah, before I go there, I'll just check if I'm recording it. Yeah, almost an hour done, so 1 more hour I have. I'll solve this rest of the 3 problems, and I'll also talk about the assignment 8 problems. Okay, so problem 8, I'll write it down. It's again very similar. Solve the problem graphically. Okay, solve the optimization problem graphically. So let's minimize z equals x minus 3 whole square plus y minus 2 whole square subjected to x square minus y less than equals 3, y less than equals 1, and xy greater than equals 0. Okay, so let me solve this. So first you have to draw the constraints. This is x-axis, this is y-axis. The level set is now circle centered around 3 and 2, right? So that's fine. And the constraint, first constraint will be a parabolic constraint. So it will go through, I think, when you set y equals 0, sorry, when you set x equals to 0, so it should go through minus 3. When you set y equals to 0, so it should go through this point, say this is plus root 3 and minus root 3. And you have to join it by parabola, and origin will be contained. And this entire region, so yeah, it's kind of open, everything will be feasible. Then you have xy greater than equals 0 and y less than equals 1. So y less than equals 1 will give you another line parallel to x-axis. Okay, and you have xy greater than equals 0. So finally you will be left with a feasible region which is looking like this. Okay, this blue shaded portion is your feasible region. Okay, so I'll just fill it up. Now you have to see where it touches the parabola, right? So y is 1. So in that case, this point is 2 comma 1. Okay, and your circle is centered around 3 2. So the circle which kind of touches this point should be giving you the minimum value, because otherwise you can keep on expanding, could have expanded the circle and you could have increased your objective function value. But here, so your circle will be something like this. Okay, so and the center of the circle will be 3 comma 2, and the circle passes through this point 2 comma 1. So that means your x star y star will be at so this is 2 comma 1, and your z value will be 2 minus 3 whole square plus 1 minus 2 whole square. So that's 1 plus 1, which is 2. So option A is the correct answer here. Yeah, so the answer is option A. So that's all about this problem. So it was again very interesting one to see solving it by graphical method. Now let me go into the 9th problem, and so only 2 of them are remaining in this assignment. So the ninth problem tells you find all the stationary points of the function fxy equals x cube minus 8y cube minus 2x square y plus 4xy square minus 4x plus 8y. Now let me solve this problem. Okay, so the function expression is written. So what I have to do, I have to take the gradient as well as the Hessian I can find out as well. But since it's a stationary point thing, so it's a function of 2 variables. So what you can do, you can write the grad of f of x or y. So first you'll be taking the partial derivative with respect to x, so that's 3x square minus 4xy plus 4y square minus 4, and then you have this one, which is 20 minus 24y square minus 2x square plus 8xy plus 8, and you have to set this to 0 0, right, for stationary points. So that gives you 3x square minus 4xy plus 4y square minus 4 equals 0, and minus 24y square minus 2x square plus 8xy plus 8 equals 0. Now let me multiply this by 2, so that gives you 6x square minus 8xy plus 8y square minus 8 equals 0, and let's add this 2 up, and that gives you 4x square. 8xy will cancel out, 8 will cancel out, so it's 4x square minus 16y square equals 0. So that gives you x square equals 4y square, and that means x is nothing but plus minus 2y. So when x equals 2y, you have 3x square minus 4x. In place of y, I'll replace x by 2 plus 4x by 2 square minus 4 equals 0. This will give you 3x square minus 2x square plus x square by 4. So that's x square and minus 4. So also that means x square equals 2, and that means x is plus minus root 2, and that means y is plus minus 2 times root 2. X is root 2, so y will be x by 2, so that will be root 2 by 2, so that will be 1 by root 2. So this gives you root 2 comma 1 by root 2 as one point, and another will be this. So this is the point. So that's one of the points. So I think that should be in the options, and then I have to check for the other condition. So that's case 1, and then case 2 when x is minus 2y. So when x equals minus 2y, what I have here is that 3x square minus 4x minus x by 2 plus 4 minus x by 2 square minus 4 equals 0. And this gives you 3x square plus 2x square plus x square minus 4 equals 0. So that's 6x square. So that's 3x square equals 2, and x square equals 2 by 3. X is plus minus root 2 by 3. That means y is minus plus 2 by 3 into half minus plus 1 by 6. Combining this 2 gives me plus minus root 2 by 3. So this total, and this is minus 1 by root 6. So these are the stationary points. So there are 4 of them. Sorry, I have closed it. Okay, so let me write this down. So option C is the correct answer. The answer is C, which is plus minus root 2 comma 1 by root 2, and then plus minus root 2 by 3 comma minus 1 by root 6. So these are the stationary points. Okay, are the stationary points. Okay, so that was all about the ninth problem. Now I'll go into solving the 10th problem. So that's the last one in this assignment. So the 10th problem tells you which of the following is are true about the function. So which of the following is or are true about the function fxy equals e to the power minus x squared plus y squared. So let me write down the options. So option A is 0, 0 is the saddle point. Option B is so saddle point is related to that point of inflection. Is a local maximum. Then you have option C, which tells you 0, 0 is a local minimum. Then you have option D, which is none of the above. Okay, so let me solve this. Okay, so the function is given as fxy e to the power minus x squared plus y squared. So what I have to do, as before, I have to take the first order derivative or the grad. So grad of fxy. So this is the partial derivatives with respect to x and y. So I think I had discussed this in the first class as well. So I think you should be able to do it. So this is the same thing times minus of 2x. And this one is same thing times minus of 2y. And now, so this is the gradient vector. Now, equivalent to the second order derivatives, I have to find the Hessian matrix here in this two-dimensional problem, right? So I'll write down the Hessian matrix, which is H of xy. So this will be the Hessian matrix. So this is equal to, so the first term is minus 2 x e to the power minus x squared plus y squared minus 2x plus 2 times, this will remain as it is. Then I have to take it with respect to y. Okay, here I have to take it with respect to x. Okay. Finally, I'll have again two terms here, minus 2 minus x squared plus y squared plus minus 2y squared times minus 2y. That will be your full Hessian matrix, and if you simplify this, it will be 4x squared let me take common then write. So it will be 4x squared minus 2 times e to the power minus x squared plus y squared. Next it will be 4xy e to the power minus x squared plus y squared. Here also it will be 4xy e to the power minus x squared plus y squared. Finally it will be 4y squared 4y squared minus 2 e to the power minus x squared plus y squared. Okay, so let's set the first order gradient vector to be 0. So this gives you minus 2x e to the power minus squared plus y squared minus 2y e to the power minus x squared plus y squared. This is a 0, 0. So the only solution that you can have from here is x equals 0, y equals 0. And in that case, your gradient, the Hessian matrix becomes h of 0, 0 equals, so that's 4x squared minus 2 e to the power minus square plus y square. So anyway, that will be e to the power 0. So that's 1. This portion will be 0 because x is 0 and y is 0. This is also 0. Last one will also be similar. Okay. So this will give you minus 2, 0, 0, and minus 2. Now, this is a negative definite matrix. Now, why is it a negative definite matrix? Because, or is it a negative definite? Just let me think about it. Yeah, so the eigenvalues are negative. The sum of the eigenvalues is the trace of this matrix, which is minus 4, and the product is the determinant, which is 4. So that means the since the eigenvalues are negative, so that you can find out by yourself. So this is equivalent to the second derivative being less than 0, right? So that means this would be a local maximum. So this will imply this is a local maximum. It's not a saddle point because everything is not 0. So option B is the correct answer. So answer is B. So which is, tells you that 0, 0 is the local maximum. So that's all about this assignment 7 solutions. So I think 2 of the problems were tricky. I think problem 5 and 6 where there was fraction powers given, and I'm also not sure whether that's correct or not, but anyway you can raise that issue later if you want to. So let me move on to the discussion on similar problems to assignment 8, and let me see how much time I have. So first I'll write discussion on similar problems. Assignment 8. Okay, so let's get started with this one. Just a minute and check. Yeah, you have some 35 minutes left, and let me see how much I can cover. Because anyway, this is a topic of discussion of next week, and I think you first have to solve the assignment by yourself, and then I'll be discussing it in the next week. But anyway, just quickly, I'll go through the problems. Okay, let me open the problems. Okay, so the first problem is, suppose for a minimization problem of a unimodal function. So let me discuss the opposite thing. Then I think you'll be able to solve the reverse problem. So unimodal function fx. I think you will know what an unimodal function is. Suppose this is a maximization problem. X belongs to, say, AB, and suppose there are 2 points x1, x2 belonging to AB. So what you can think of a graph of the function. So it's an unimodal function. So suppose the maximum occurs somewhere here. Okay. So this is your fx, this is your x1, this could be your x2. Okay, so this is how your curve look like. Let me name it something else, x1 prime, x2 prime. Okay, so now let's pick up 2 points, x1 and x2. Okay, suppose here it's my x1, here could be your x2. So in that case, this is given. So now case 1 could be I give you fx2 is greater than fx1, which is the case in the curve. So which region you can eliminate? So also this is A, this is B. So you know for certain that if fx1 is less, then everything to the left of x1 will also be less. So you can eliminate this portion, ax1 portion. And also now suppose I have given you fx2 is greater than fx1. So it might happen that you are also in this portion, right? So x2 can be here also, because in that case also fx2 is greater than fx1, but your x2 is not somewhere here or somewhere here, but you don't know for certain where it lies, right? So in that case what happens is that you can, so the maximum lies within x1 and b when fx2 greater than fx1. Okay, and suppose case 2 I give you, it's fx2 equals fx1. So in that case what happens is that, and x1 is not equals to x2, so it will be in the other portion, right? So it's somewhere here the x2 will lie, and this is where the equal values comes in. And in that case you can eliminate two regions, right? Because in one side it will be decreasing, in other it will be again decreasing. So in that case you can say that the maximum lies within x1 and x2 when fx1 is equals to fx2, and case 3 could be something else, which is fx2 is less than fx1. So it might happen that x2 is on this side, so but that's not possible because typically what happens is that x2 is greater than x1, or it might happen it's in this region. So in that case what you know for certain, that after x2 and within x2 and b there will not be anything, because your x1 could be here as well, and this could be your x2, so you cannot eliminate what is to the left of x2. So in that case the maximum lies within a and x1 when, so if x2 is less than fx1. So you'll find a similar problem with a minimization problem, and you have to check which one is the correct answer, right? So that's all about problem 1. Problem 2 will be to find a minimum of function within the 10% of exact value using interval halving method. So probably I'll have a different problem here. Okay, so interval halving method. So I'll change the expression of the function. So let me take it as x times x minus 4. So minimization of this x belonging to 0, 1. So this is within 10% of exact value using interval halving method, which I have already written. So let me just quickly check what will be the minimum within this range. Because it's a bounded problem, so anyway, let me do it by the other way. Sorry. So when you have 10% accuracy, so that means I think in the interval halving method what you have is so at every step you kind of half your interval. So these are the length of the interval. So to begin with, the length of the interval is sorry, this is your L naught, and then in the next, suppose you pick this one, so this is your L1, and probably this could be your L2. So keep on doing this, right? So your L1 by L0, let's say half. Okay, so let me check. Okay, so actually L0 and L1 could be the same. Yeah, so what you can do, you can take it as this. This could be your L2, this could be your L3. And in that case, this should be less than equals to say 10%. So that's 10 by 100. And you can write the expression of ln like half times minus 1 by 2. And when n is 2, so it depends on how many points you are picking. Okay, I think I made one mistake. Okay, so when you're picking 2 points, okay, so when you're picking 3 points, so then this is exactly half. Then when you're picking, evaluating at 5 points, so that's different. Okay. Okay, when you're picking 3 points, yeah, so it will be slow. So that's exactly half, and picking 5 points, it's 2, that's 1/4. Yeah, so you make it as 1/4. Okay, so this will be half. Okay, power in minus 1 by 2 less than equals 1 by 5. So you can take the logarithm if you want, or it's nothing but 2 to the power 2 by n minus 1. Oh no, it's not correct. Okay, so this will be okay. Let's reverse it, so that should be easier to do. So that is 5. Then that means n minus 1 by 2 it's since it's so n is 6 will not give you the desired result, so n has to be greater than equals 7. So that's the thing, that's the first step, and your interval is given as, so AB is 0, 1. So step 1 would be to pick x1 equals 0.25. So x0 could be your 0.5, which is the midpoint, and x2 could be your 0.75. And then you have to evaluate your functions, and you have to keep on repeating it, and finally we'll get the solution. Okay, so evaluate the function values. And proceed to the next step. Okay, so I'm not solving the entire thing because it will take some time to solve it, and I'll anyway solve it next week. Okay, so third problem is again similar. This one is exhaustive search method. Third problem could be exhaustive search method. So in that case, what happens is that suppose 10% of exact values. So in exhaustive search method, you will do similar things, but it's half of, say, ln by L naught less than 10 by 100, and here where ln is 2 by n plus 1. So that's L naught. So that's 1 by n plus 1 less than 1 by 10. N plus 1 greater than equals 10. N is greater than equals 9. So in exhaustive search method, you have to take, say, 9 points, and your xi values could be going from 0.1, 0.2 until 0.9, and you have to just get the solution where it is maximum or minimum. So that's a simple exhaustive search method. Then the fourth problem, it's probably similar, so it tells you dichotomous search method. Okay, so suppose here I am giving you 20% of accuracy, and suppose I tell you find the number of iterations required. Okay, so let's try and do that. So in this problem, ln is nothing but L naught by 2 to the power n by 2 plus, say, delta times 1 minus 1 by 2 to the power n by 2, and you can say delta is very small, and in that case what happens is L naught is 2 to the power n by 2. Okay, so with 20% accuracy, what you will have is half ln by L naught is then equals 10 by 100, 20 by 100. Yeah, just a minute. Yeah, so it's nothing but it's now 1 by 5. Okay, so in that case, S3. Okay, by 2 is greater than or equals 2, n is greater than or equals 4. So this is the minimum number of iterations. Okay, so just let me check one more thing. What's done in the PPT? Okay, so in the PPT will have similar things as well. So yeah, go through the lectures and the presentations as well. So I think I'll be able to answer it. Okay, so the fifth problem is the interval of uncertainty after the first step of dichotomous search method for minimization of this with x belongs to this and delta. So suppose in the fifth problem I give you x belongs to 0, 1 and delta equals to 0.01. So how we will get the interval of uncertainty after the first step? The first step. Okay, so in this problem what I have is, so as you know, ln is L0 by 2 to the power n by 2. So this is a dichotomous search. Okay, plus delta times 1 minus 1 by 2 to the power n by 2. So now let's calculate these things. Okay, okay, so that's the length of the interval. Anyway, so what you can do, and x1 equals a plus L naught by 2 minus delta by 2. x2 is a plus naught by 2 plus delta by 2. So a is 0 here and L naught by 2 is the length of that interval, which is 0.5 minus say 0.01 by 2. So that will be 0.005. Okay, so that's something like this. Here it will be okay. Then you can find the minimum, where the minimum lies depending on the function given. But actually, yeah, interval of uncertainty. So depending on the function expression, so it's the same as the region elimination technique. Find the interval of uncertainty. Okay, I'm not going into the details of the rest. Okay, so next is reduction rate of the initial interval in the Fibonacci method. So yeah, so the Fibonacci method, okay, so let's see. The reduction ratio is nothing but ln by L naught. So get the expression of ln and find this. So I think you'll get it directly from the slides. So I'm not writing down. For the Fibonacci method. Okay, so that's the 6th problem. 7th problem is on golden section search method, where you have to find gamma. Okay, golden section method. Find the value of gamma. So I think this is also directly from the lecture videos. I'm not giving you the answer from the lecture videos. Okay, so let's check the rest of the 3 problems. Okay, for 10% C of, okay, so the next one, the 8th problem is asking you which method will be preferable for the 10% accuracy, Fibonacci section or the golden section, or is it equally preferable? So I think in this problem what you have to do, you have to check for how many points or minimum iterations required for both the cases, and the one which is having lesser number of minimum iterations required will be preferable. So check for minimum number of iterations required for both the methods the one which is giving you the lower, just giving you the lower number of iterations will be preferred. Okay, so that you have to do it on your own, so I'm not giving you the answer. So let's quickly discuss 9 and 10, and then I'll wrap up for today. Okay, so the interval of uncertainty after the first step of Fibonacci method for minimization of this. Okay, so it's again very similar. So it's the interval of, I think this assignment is also very easy and you can get it done very quickly. So I'll discuss the detailed solution next week of Fibonacci method. So the function expression could be something so that I'm not giving you, but yeah, quickly let me check what you can do here. So typically what you have to do is say some x1 equals a plus x2 equals b minus. So this is the typical approach that you would adopt in this method. So suppose my n is say 6 or something, then you have to find x1 and x2, and your x0 could be sorry, this is not x0, this is L0. So L0 will depend on what's the value of a and b, and this Fibonacci numbers you can find out, and after that you can find out x1 x2. You can then calculate fx1 and fx2, and then compare and check which region you can eliminate and which is the first interval of uncertainty. So that is pretty simple. Then I have the 10th problem. So the 10th problem is again related to, suppose, a quadratic approximation problem. So that's given. Then so let me check. So px is a0 plus a1x plus a2x square. So this is the quadratic approximation of fx. So now, depending on the values of a1, a2, a0, you have to decide whether it's in quadratic interpolation optimization method, which one is required. So again, I think this is directly from the class. So yeah, I think you can solve it on your own. So this will be discussed. So it's almost time as well, so I'll be discussing this in the next class. So next class, full solution of assignment 8, and you have to, I think, submit it by this Wednesday. And similar problem discussion of assignment 9. So that would be your week 8 class, week 8 TS session. Okay, so that's the agenda for the next week, and with that, let me see if there was anything else to discuss. Okay, so it's I have just 1 minute. So discussion forum is, I'll just wrap up with that. So I think discussion forum, there was 2 doubts. Yeah, doubt 1 was on drawing the level sets. So that's cleared now, so that's fine. Then doubt 2, assignment 5 question. like question 1, I think objective function, but the solution is present in one of the options. So this is also fine. And yeah, ask. So if you have further doubts related to this week's content or anything, so ask doubts in the discussion forum, and also you can use this TS sessions regular from 3 to 5, and you can drop by and ask your questions as well. So that I'll wrap up for this week, and see you all next week, and hope you'll go through this video posted on YouTube later. And also, yeah, do ask questions in discussion forum, or you can also join during the regular time from 3 to 5. So yeah, thank you all.